Hi everybody, welcome to another video in Calculus 3. We go to section 13.5, lines and planes in space. So a line is a one-dimensional object. So we might have a point, we can go forward, we can go backward. That's one-dimensional object. A plane is two-dimensional object. So we can go forward and backward, left and right. Just think about the remote control car, for example. You only need to go backward and forward, left and right. With those controls, you can control the car moving anywhere in the plane. So a plane is a two-dimensional object. So we have a one-dimensional object and a two-dimensional object. In space will be three-dimensional space. So we have one-dimensional object in three-dimensional space and two-dimensional object in three-dimensional space. That's what we have in this section. Right, equation of a line. Equation of a line passing through a point in the direction of a vector is given by this. So we can write equation of a line in this form. Or R is the x, y, z, and R sub 0 or R naught is x0, x0, y0, and z0. So this is a particular point. It is a variable. So we have both equations. Right. Now it is mentioned that a line is the one-dimensional object, right? So in which case we have one parameters. One-dimensional object requires one parameters. And in this case we have the parameters from negative infinity to infinity, meaning that we can go indefinitely on both sides. Right. Now, so we did say that these are the variables. Those are constant. Now if we combine all the first components, x0 plus t times a, and then the second component, y0 plus t times b, and the third component, z0 plus t times c, and we matched with the first, second, and third, we have the parametric equation written in this form. And because parametric equation, we still need the parameters in some certain domain. Right. So bottom line, what do we need for the equation of a line? Two things. First, we have to have a point, and then we have to have a direction. So a point and the direction will define a line. Right. So next, find equation of a line that passes through the point. So we have a point here, and it has the direction of 5, negative 3, and 1. So the direction, the vector pointing that way, 5, negative 3, and 1. Right. So just find the equation of that line. So pretty straightforward. Equation of a line, r equal to r naught plus tv. This is the whole line, so t between negative infinity to infinity. R can be written as r or just x, y, and z. R naught is a point on the line. We have a point here. We write a point in this notation. And then plus t times v is the vector. Now we can multiply t to all of this and then combine the components by component. So the first component have 1 plus 5t, 2 minus 3t, and 4 plus t. Right? So we just write x, y, z equal to that, for t between negative infinity to infinity. Next, find the projection of this in the xy plane. Now this is a projection. We're not talking about the intersection, completely different things. Now we have a line, let's say a line somewhere in here on space. The projection of that is on the xy plane is like that. You see, it's just a shadow of it. You don't see it. They're not on the same line. But the projection of this is going to be that on the plane. Simple enough. Here we see that it is on the xy plane. On the xy plane, z is equal to 0. So what we do is we're going to let z equal to 0. We don't let for plus t equal to 0 and so for t. We're not shown for the intersection. We just find the projection. So this is a projection, not an intersection. Intersection, we do let for plus t equal to 0 and so for t. This is projection. So in that case, we say the projection in the xy plane will be in this form: x, y, and z, where we have 1 plus 5t is still x, 2 minus 3t is still y, but z is going to be 0. So that's just a projection, not intersection. Right, because t is still between negative infinity to infinity. We know that still here. Right, that means x equal to 1 plus 5t and y equal to 2 minus 3t. Now we have two equations, and both of them in terms of t. So we can solve for one of them in terms of t. So let's solve for here. X equal to 1 plus t, so x minus 1 is equal to 5t. So t equal to x minus 1 over 5. And we can substitute this into t here. So 2 minus 3t is going to be equal to 2 times x minus 1 over 5. I wrote that completely wrong, didn't I? So substitute for t, so we have 2 minus 3, like that. So put that in for t, that's what we have. So we have 2 minus 3/5 x minus 1, multiply it out, 2 minus 3 over 5x minus negative plus 3 over 5, and 2 plus 3 over 5 is 13 over 5, so we have negative 3 over 5x plus 13 over 5. And so we have the equation y equal to negative 3 over 5x plus 13 over 5. Right, so that's simple enough. Next, let L be a line that passes into the point. So now instead of have a point and the direction, we have 2 points, which is perfectly fine, as long as the 2 points are different. If we have 2 identical points, we don't have a line. We have a lot of lines, but if we have 2 points, P and P0 and P, suddenly we can just find a vector connecting them, right? So that should be no problem. So we're going to use the point here, this point, and then we will find the vector PQ is going to be the direction, right? So vector PQ, no, there's no Q, right? So vector P0, P1, right? Vector P0 and P1 is equal to the head minus the tail, the final minus the initial. P1 for 2 and negative 1. Subtract P1, P0, actually P1, either we use P0, P1 or P1, P0. It doesn't matter the direction. You can point this way or you can point that way. We still generate the same line. And we subtract them and we will have 4 minus -3, that would be 7. 2 minus 5, 2 minus 5, minus 3, and minus 1 minus 8 is minus 9. So that is the direction vector, and then we will put in the equation of the line r equal to r naught plus tv. V is a vector where t all real numbers. Right, the point we can use either one of them. I will use this one. I said, even though the point here you write in this notation, but I mentioned more than one time before, the notation of a point and a vector, it could be the same. At higher level, we're just going to use the parentheses. But for now, sometimes we distinguish the vector, we just write in that form. But as long as we have something that has 3 components, it could be a point, it could be a vector, it doesn't matter. Vector is 7, -3, and -9. Then put them together. So we have r equal to r, the point, combine the first component, -3 plus 7t, 5 minus 3t, and 8 minus 9t, where t is between -infinity to infinity. Right, so that is equation one line. Now find the intersection, the projection onto xz plane. Xz plane, y is equal to 0. So the projection onto xz plane, we have this form, x, y, and z equal to x is still -3 plus 7t. Y will be equal to 0, and z equal to 8 minus 9t. Of course, t is still from -infinity to infinity. From here we can let x equal to that and z equal to that, and then we eliminate t. So pretty much like what we did earlier. So x equal to -3 plus 7t, and z equal to 8 minus 9t. And we can solve for x, solve for t in terms of x. So 7t equal to x plus 3, and t equal to x plus 3 over 7. We can substitute this into this t. So 8 minus 9, x plus 3 over 7. Right, multiply out 9 over 7, x plus 3, 8 minus 9 over 7, x, 9, 3 times 9, 27 over 7, 8 minus 9, 27 over 7. Right, 29 over 7. So we have y equal, there's no y, there's z, right? Z equal to -9 over 7x plus 29 over 7. Right. I need to reset the computer, the calculator. It didn't show. Right, so that. Now, more examples. I'll find the equation line segment between those 2 points. Now, different here is very subtle, the line segment. So, meaning that we do not have the line that is extended indefinitely. We only have a part of the line. So how do we do that? We know P naught and we know the direction P naught to P1, right? So in general, let's just start with, let's say the equation is going to be equal to, we go from P naught, and then the direction is P naught P1, right? Of course, every time we do that, we have to know what is T, right? That to be determined. Now, if we write that P naught P1 is the vector, we can say T P1 minus P naught, right? Multiply it out. P naught plus T P1 minus P naught times T. Combine like terms. We have 1 minus T times P naught plus T times P1, right? Notice now, if T is equal to 1, we have the point P1. If T is equal to 0, we don't have this, and we have just P naught. So at T equal to 0, the point, the equation is equal to T equal to 0, so we don't have this, and we have 1 minus 0, so we just have P naught. At T equal to 1, we have R equal to 1 minus 1 is 0, and 1 times anything is itself. Right. So we have at 0 and 1 we have the endpoint. So bottom line is the equation of the line segment connecting the two points P naught to P1 is R equal to P naught plus T P naught P1 is a vector where T between 0 and 1. So initial point at 0, final point at 1. So we just like that. So this is the equation of a line segment. We will see this more than one time later. Right. So just find a vector P naught P1 P1 minus P naught P1 0, 5, and 2, P naught 3, negative 1, and 4. Subtract them, we have as a vector 0 minus 3, 5 minus negative 1, so it will be 6, and 2 minus 4 minus 2. So minus 3, 6, minus 2. And now we have the equation is equal to, we can use any of this. Actually we cannot, this have to be P naught. So this is the line segment, so more restriction on that, so I have to use P naught if we use the vector P naught P1. 3, negative 1, and 4 for P naught, and then the vector is negative 3, 6, and negative 2. And every equation we should have the limit for T so that's what we have. Next we have another application, distance between a point and a line. So see what we have here. So what we have is a line as you this color. For a line we do need a point That point will be P. And we wish to find the distance from a point Q that is not on the line. So point Q is way over here. This is not on the line. What we're trying to find is the distance, which is the perpendicular line to it, and we're trying to find this length here. So in that case, let's just connect PQ. And remember, every time we have a line, we will have a point and a direction. So we do have a direction here. That is V. Of course, we can have the vector PQ too. Now, from that formula, let me derive here. Distance is equal to vector V cross vector PQ over the magnitude of vector V, right? By the definition of the cross product, V cross Q PQ is going to be the magnitude of V, the magnitude of PQ, and then sine of an angle between them. And we did mention that whatever the angle is, make sure all of this is positive because the magnitude is positive. And of course we cancel this, so it's just equal to PQ, magnitude of PQ times sine theta. So magnitude of PQ times sine theta, which is of course is going to be D, right? Because sine is opposite over hypotenuse. So that's very straightforward there. Right, so it's easy enough. Except I should leave more space on this problem. Right, for the distance between this point and this line. Right, so we have x, y, z is equal to just that. So let's say x, y, z is equal to t 2, 1, 2. So we certainly have a vector direction here. That is vector v this is vector v. So where's the point? Actually, if it's given in this form, then obviously that is a point, right? Now, actually it's easier than that. We just let t equal to anything will give us a point. We can let t equal to 0, 1, 2, 3, doesn't matter. One value for t give us 1 point. So why don't we choose t equal to 0? T equal to 0, we have a point. And let that point be p equal to 0, 0, 0. So the point 0, 0, 0 belongs to the line. And in that case, we can have the vector PQ. So vector PQ is equal to Q minus P 1, 0, and 3. I should leave a lot more space than this. 0, 0, 0, 1, 0, and 3. And then we use that formula for the distance of a point to a line. We have V, we have PQ, we have everything. So first let's find V cross PQ. So V cross PQ. Or PQ plus V, it doesn't matter because we have the magnitude. It doesn't matter which one cross which one. Could be V cross PQ or PQ plus V. I, J, K. I try to write very small here. Vector V 2, 1, 2. Vector PQ 1, 0, and 3. Right? It's mentioned, we just do it like this, right? So to cover I, we have 1, 2, 0, 3 for I. J two two 1 3 J 2 1 1 0 K. So in that case, 3 minus 0, so we have 3 for the first component, 3. And then for second component, we have 6 minus 2 is 4, but with the minus, so minus 4. Six minus 2 is 4, so minus 4. And then 0 minus 1. So that is the cross product, V plus PQ, V cross PQ. And then we have the distance formula, V cross PQ over magnitudes of vector V. So the magnitudes of this vector, 3 square, negative 4 square, 1 square, over vector V, magnitudes vector V, square root of 2 square plus 1 square plus 2 square. Right, 3 square is 9, 4 square is 16 plus 1 square root of 26. And square root of that will be 9. So we have square root of 26 over 3. And that's what we have. Simple enough, straightforward. Right? Right, next. Find the point at which the plane and the line intersect. So this is an intersection, not a projection. So intersection meaning that x have to be equal to x, y equal to y, and z equal to z, which means z have to be equal to z. Of course, if we have that, we can say that t is equal to 10. Then at 10 equal to t, we have the point 2 times 10 plus 1 minus 10 plus 4, and t is 10 minus 6. So we have the point 21, negative 6, and then 4. We just write that as a point or a vector, it doesn't matter. But they want the point, so yeah, that is the point of intersection. Right, so point of intersection, all the x equal, all the y equal, and all the z are equal. And so we make them z equal to it, and then we show t is equal to 10. Put 10 here, 21, 10 here, negative 6, and 10 here is 4. So that is the point. So pretty straightforward, right? So a line and a plane. Usually if we see there is a plane like this and the line here, the line is extended indefinitely. So usually there will be intersection between a line and the plane. There will be a point. Now, if I give you two random lines like this, they may or may not be the intersection. It is the intersection, but we see in different perspectives. It's not. So when you see two lines, the chance for them to intersect is usually less than the point and the plane. Of course, unless they could be parallel, or they can be skew line. Skew line, they have no intersection, but they are not parallel. So on the rare occasion there is the intersection, and extremely rare occasion the two lines are identical. But regardless of any of those cases, when we said if there is an intersection, the x equal to the x, the y equal to the y, and the z equal to the z. So let's try that. We have x equal to 2 plus 3t here, and that have to be equal to 4 plus 2x. And then next, y equal to 3t have to be equal to negative 3 plus 3x. And then z equal to 1 minus t have to be equal to negative 2s. All of these three have to occur. So look at the first equation. It's not the x here. I move the s and the t on this side and the number to the other side. So I have 3t minus 2s equal to 2. And then next, I have 3t minus 3s equal to 3. Right. I'm just ignore the z for a moment. I'm just going to solve for this equation first. To solve in the system equation, like elimination, substitution, and we use elimination. Let's multiply the bottom equation by negative 1. Did I forgot that? This should be negative 3, right? 3t minus 3s equal to negative 3. So multiply the second equation by negative 1. We will have negative 3t plus 3s equal to 3. And then we have 3t minus 2s equal to 2. Combine like term that cancel out, and we have s equal to 5. Now if s equal to 5, we can just put it back in here and we solve for t. So 3t minus 2, and then we put 5 in there for s. That's supposed to be equal to 2. So move the 10 over, that gives us 12. So 3t is equal to 4. So give us 3t is equal to 12. So that gives us t equal to 4. So s is 5, t is 4. Why don't we put it back here and check? So this just check, because two equation, two variable, that's a fair game. We should be able to solve it. The third one may be redundant. We might not need the last one. So just check to make sure that it works. So t equal to 4. So 1 minus 4. Is that equal to negative 2 times s is 5? And the answer is no. So those first two equations we solve for s and t, but that doesn't work. So here we say no solution. Which means no intersection. Right. Before I go further, I just want to show you quickly on how do we do this on calculator. Right, this is in linear algebra, but probably you see this before. You see when we hit second and that button, second matrix, and we have this. Go to the second tab, math. Go down to option RREF. Right. Now, we hit alpha, zoom, if your calculator have this option, when you hit alpha zoom, the bottom menu pop up and you see the matrix, which is good. This one will have the 2 rows for 2 equations and 3 columns, 2 coefficients and 1 constant. So 2 by 3, right? And then the coefficient are 3, negative 2, 2, 3, 3. If you use a negative, use this button, negative 3 and negative 3. And just hit enter. So the first one is 4, the second one is 5. So that's how we solve the system of equation. Right, let me just write out. On calculator we will use RREF and reduce row echelon form apply to the matrix 3, negative 2 and 2, 3, negative 3 and negative 3. If we do that, we have the vector 4 and 5 as the answer. RREF meaning reduce row echelon form. Right. By the way, if you're using the different model of calculator, you cannot do this. Hit second matrix and just go to edit and then here we enter the matrix 2 by 3 and we enter the same thing 3. We have to hit enter in this environment, negative 2, enter and 2, enter 3, negative 3 and negative 3. Right, then we do the same thing. Reduce row echelon form, but then we hit second matrix and we earn the names. We're going to use matrix A and it gives us the same thing. Right, so if we cannot enter the matrix directly in the home screen, we have to save that. We have to store that at the matrix first and then recode it later. Right, we use that more than one time. Right, next we have this same thing, intersection of these two lines. So once again, if there's an intersection, x equal to x, y equal to y, and z equal to z. So x equal to x. 3 plus t supposed to be equal to 2s. Uh, 4 minus t is equal to minus 1 plus 2s. And then z equal to 5 plus 3t supposed to be equal to 4s. Right, we only need 2 of this to solve for s and t, 2 variables, 2 unknowns. Usually we have a solution. Right, let's move things around. T plus 2s. To move to the other side, it becomes minus 2s. So t minus 2s equal to minus 3. And then move the 2s over, we have negative t minus 2s. Move the 4 over, it's minus 5. Right. Right, I will use the calculator here, even though the elimination is extremely easy thing to do. So second matrix, go to math and go to option B. Right, alpha zoom if you can do this. Again, 2 row 3 columns, so that's good. 1t. Don't hit enter here, just hit the next arrow. -2, -3, -1, -2. Again, use this negative, don't use the subtract here. And -5. And then you have 1 and 2, meaning t is 1 and s is 2. So we have t equal to 1 and s equal to 2. So we know which one's which. So because we have t in the first column and s in the second column, so one is s. The first one is going to be t. Yeah, the first one is going to be t. The second one is going to be s. So that's why we know which one's which. And then we go back here and check with the last one because it may or may not work. So we have 5 plus 3t is 1 and s is 2. So I have 8 equal to 8. Yes, that checked. So the intersection will be at t equal to 1 and s equal to 2. So intersection is at t equal to 1 and s equal to 2. And at t equal to 1, the first equation becomes x equal to 3 plus 1, y equal to 4 minus 1, and z equal to 5 plus 3 times 1. So pretty much we have x, y, z, the point of intersection, equal to 4, 3, and 8. Or we can put 2 in here, which is give us 4, 3, and 8. Either we put t in here, t equal to 1 in here, or s equal to 2 in there. Right. Next we have 5 equations align that in R2, which is in the plane, that passes to the point 2 and 3 and is perpendicular to this line. Right. So this is interesting problem. We'll do this in at least 2 different ways. So let's see how it works. So we have the point 2 and 3. 2 and 3 here. And we have a line. This is the point. And then this is the line. Point 5 and 1. And we have 1 minus 3t. So the vectors 1 to the right and -3 down. So we talk about this vector and we talk about this line. So that is equation 1 line. But we do have the point of 5 and 1 when t equal to 0, and then the direction 1 and -3, meaning 1 to the right and -3 down. Right, so we have that. What we're trying to find is the equation of the line that's perpendicular to it. So we're trying to find the equation of this line. Where it is perpendicular. Right, so how do we do this? I said there's more than one way to do it. So first, let this point be the point P, and find one. Let that be the point R. And the point of intersection here, let that be Q. Right, so we have 2 points. We can find a vector. So suddenly I can connect the vector PR here, right? So we can find the vector PR. And then we do know the vector 1 and negative 3. So because we have the line that go to this point, and the direction we can say is the vector V is 1 and negative 3. So it's pointing in that direction. So we have PR, certainly can find that vector PR, and then we can find the orthogonal projection of PR onto V. If we use the shadow of PR, project that onto the line, it will be QR. So the first important fact about this is QR is equal to the projection of PR onto V. That's the first thing. Vector QR, projection of PR onto V. So first we find a vector PR, which is R minus V, R minus P. The point find 1 minus P 2 and 3. So it will be 5 minus 2 is 3 and negative 2. So vector PR is 3, negative 2, meaning 1, 2, 3 units to the left, 3 units to the right, and then 2 units down. That's with 3 and negative 2. So that's about right. Right, let's find the orthogonal projection, QR, projection of PR onto V. So orthogonal projection, if we go back to the cross product, the previous section, it's going to be the dot product of PR. No, in the section 13.3, the dot product. Dot V over V dot V times V. Vector PR 3 negative 2. Vector V 1 and negative 3 over V 1 and negative 3 1 and negative 3 times, there's no dot or no thing here, 1 and negative 3. Alright, dot product, 3 times 1, 3. Minus 2 minus 3, that's 6. 1 times 1, negative 3 times negative 3. So we have 9 over 10 times 1 common negative 3. Multiply that inside, so PQR is equal to vector 9 over 10 minus 27 over 10. Right, that's good to know, but how did that help us? What do we want though? We want to find the equation of the line, in this case the line QR. That line is going to be QR. PQ, the line that we're trying to find. So we were trying to find the line PQ. Right, to find the line PQ, we need two things, the direction and the point. We have the point, and the vector PQ will be the direction. The problem is we don't have the vector PQ, right? We don't know the point Q. That's the point. So how do we get the point Q? Notice that is what we have in the triangle rule. or the head to tail rule, we have the vector PQ plus vector QR is equal to vector PR. Remember the head to tail method. Head to tail. So P plus Q and Q, P to Q and Q to R is the same as P to R, right? So that's head to tail method. So we have QR, that's good. We have PR, that's good. We can solve for PQ. So from here we can say PQ is equal to PR minus QR. PR 3 and negative 2. Subtract QR 9 over 10, negative 27 over 10. Right. So we have 3 minus 9 over 10. Right, that's 2.1, which means 21 over 10. And then negative 2. Negative, a negative, so that plus 27 over 10.7, so we have 7 over 10. Right. That's good. So certainly we can use this vector. However, I remember we need a vector in direction PQ. It could be extremely short or extremely long. As long as they point in the same direction, the magnitude doesn't really matter. We focus on direction here. So for the line PQ, we use the point P, and let's use, instead of use vector PQ, we choose the vector to be 10 times vector PQ. Why do I do that? Because 10 times this eliminate the 10, we just have 21, 7, which is better. Like I said, any vector point in that direction is good. So we have R equal to P, what's the point P, 2 and 3. I just write it's a point, doesn't really matter. The vector here, we're going to use 10 times that, 10 times this. We can use 21 over 7. Or we can just use that point, it doesn't really matter. I try to use this because I simplify the calculation. Just choose any vector point in that direction. It's good. Doesn't have to be exactly PQ. It will be 10 times PQ, or even better yet, I should say if you divide by 7, so we have 3 and 1. I could choose 3 and 1 if I choose to. So we have the equation 2 plus 21t and 3 plus 7t. So that is one way to do it. Right, so we use kind of a vector or geometry to do that. Next, what we use is the grade school. I mean, in high school, we can just find this problem without any problem. Right, let's say it. If we're in high school, when we have the equation of a line, we have a point. Instead of direction, we have the slope instead. So a point and the slope. So for this line, the point is find 1 and the slope 1 unit to the right and then 3 units down. So the slope in general is rise over run. So this line we have the slope equal to rise instead of up, this is -3, so we go down -3 over 1, so -3. So this is the slope of this line, -3. So we have the slope equal to -3. So it's good. So how is the slope of this line relate to the slope of that line? So back to high school. What do perpendicular lines, what are the slope of perpendicular lines? So we have a slope of perpendicular line so the slope of those lines are opposite reciprocal, or the product is equal to -1. This is the fact that we have been back in high school. So the slope of perpendicular lines are opposite reciprocal, or the product is equal to -1. Either way, the product of the slope equal to -1. So if this is -3, so the slope of the line PQ, so line PQ the slope equal to negative reciprocal, so it's going to be reciprocal of that, so -3 over 1 will be flipped, and this is opposite, so this is 1 over 3. Now if that is the slope, the equation of a line is y equal to mx plus b is the equation of a line. Now we have the point 2 and 3, so at x equal to 2, y equal to 3, I'll put x and y in here, 3 for y, m is 1 over 3, we do know that. X is 2, and b, don't know, so it's 5. So we have 3 minus 2/3, 3 minus 2 over 3, that will be 7 over 3. So b equal to 7 over 3. So we have b, and we have the slope, which is m. So we can substitute this 2 into the equation. So we have y equal to 1 over 3x plus 7 over 3. Right. And they will say, are they the same? Right. Let's verify that. We only have this much space left. Well, maybe enough. So in this equation, we have x component equal to 1, 2 plus 21, and y is 3 plus 27. So x equal to 2 plus 21 t, and y equal to 3 plus 7t. Right. And then suddenly we can solve for t here. So we have x minus 2 over 21, and we substitute that in here. Uh, 7 over 21 is 1/3, so I have 3 plus 7 over 21 is 1/3, so we have 1 over 3x, and 1 over 3 minus 2, 2 over 3. So we have 1 over 3x, and 3 minus 2/3 is 7 over 3. So yes, they are the same. So there's a lot of ways to approach to a problem, especially this problem. We see 2 different ways here. There's one more that I can think of right away. Right, so first, remember we have the vector, we don't know the vector PQ, right? But what we can do is, we have the vector V, that direction, right? We have the vector PR, this direction for PR. Now remember, every time we have two vectors, vector has no location, so let's just move things around. So vector PR and vector QR. So we have two vectors like that. It doesn't matter, you can just move them. Now if you have two vectors, do the cross product. The right hand rule give us the vector like that, right? So now we have do the cross product between PR and QR, going to give us this vector that is perpendicular to the plane here. And after that, we do the cross product of this one and the cross product of PR once more time. We use the right hand rule. It's going to be this vector. And that vector is vector parallel to PQ. So we have it. So bottom line is, what we do is, first let vector W be the product of PR and vector V. So in that case, when we cross those two, we're going to have the vector W pointing up like this. And then next, we take that vector and we're going to cross with the vector V. We're going to have either we have the vector pointing that direction or this direction. Then we do the vector W cross the vector V. This vector is parallel to vector PQ. And so that gives us the direction for the line PQ. Yeah, so we just do two cross product. That works. Or you use orthogonal projection, also work. Or just use the simple algebra, also work. Right, so those are align one-dimensional object. It is one-dimensional object, so we have one parameter, t. Right, now we have two, which is align. Right, this looks like a long section. Go over a lot of things though. Right, a plane in R3. So a plane is two-dimensional object in R3. So remember, for the equation of a line, we write R equal to upon plus V. So it is one-dimensional object. We need one parameters in any direction. Right. Now, if we want the equation of a plane, we can actually write like this to R equal to R naught plus TV and then S W. So we're going to have two parameters T and S for two vector V and W. So for example, if I have two directions like this, one up and one to the right. If I want to go here, I will go up this much and will go right this much. So the combination of up and down, or the combination of up, down, and left, right, allow you to go anywhere in the plane, right? Like just like the example we said, the remote control car. When you control a car, you can either go up and down, forward and backward, left and right. In that case, you can travel anywhere in the plane, and that's all we need, two direction. But if we have two direction right like this, yeah, that might be a little bit of work. So instead of right like this, think about differently. If we have two direction, right, one is up and down, one is left and right. So why don't we do the cross product? The cross product will give us a vector perpendicular to those two. So that's why we only need one vector that is perpendicular to a plane. Right, so a plane in 3D. we need a point and a vector n. Now this is n, it's not the direction vector anymore. We set n, any point in the plane is orthogonal, so set a point orthogonal to that. So what we need is any point on the plane and the orthogonal to this. Think about this. If my hand is a plane in any direction, right? And I just have the normal vector, so characterized by the normal vector here, will give us a plane. I do need a point though, because vector has no location. I kind of have to know a point on the plane, so the plane will be here and not here. So see the parallel, so you can have the plane here or plane here, it doesn't matter, still the same vector, but I need to know one point so I can exactly pinpoint the plane. So I said just one vector here will characterize a plane. So what we need for a plane is the point and the normal vector. Normal is also meaning that it is orthogonal to a plane. So there's different ways, right? Previous example, we have two lines perpendicular. When we said perpendicular, we refer that to be on the same plane, two lines. When we talk about orthogonal, it may be like this, two vectors in space. Those are orthogonal, right? But they do not have any intersection. Think about that. So it is like this, no intersection, and still perpendicular, right? And now when we talk about normal, it is between a line or vector and a plane. So we use normal. So it's also 90 degrees from that point, from that vector to every vector on the plane, right? And we have the normal vector. So since this vector is orthogonal to every vector on the plane, we have one point P and any point P naught. So let's say we have this vector from a point, fixed point P naught to P. This vector is orthogonal to n. So n is orthogonal to any vector on the plane. Because it is orthogonal, the dot product is equal to 0. So when we multiply it out, P naught P is going to be P minus P naught, and the dot product with the normal vector is 0. So different form, we can write like this, or this, or that, or that. A lot of different form. But like I said, what we do need two things, a point and a normal vector. So when you change in the vector, you change in the plane, right? Now for equation of the plane passing through the point with a normal vector, so this one is obvious. So we say is that normal vector is orthogonal to everything so that normal vector is -1, 2, and 3. Vector PQ is P minus P naught, right? So P can be any point. Just be X, Y, and Z. So we will have X, Y, and Z. That is P minus P naught equal to 0. Yeah, so P naught P equal to P minus P naught. Right. So -1, 2, and 3. Later on, we just say X minus 2, Y minus -3, and Z minus 4 equal to 0. Multiply it out. Negative X minus 2 plus 2 times Y plus 3, and plus 3 times Z minus 4 equal to 0. That is the equation of a plane. Usually I prefer to write this one. And so where we can extract the point easily, the point will be those two. We give us the point 2, -3, and 4. And then the direction -1, 2, and 3. This is the vector -1, 2, and 3. Not the direction vector, but the normal vector. So from this equation, we can extract those information easily. And with this information, we can write the equation easily. Bottom line is, one point, one normal vector will give us a plane. That's what it said here. Next, find an equation of the plane passing through the point P, Q, and R. So we have 3 points P, Q, and R. So let's say we have 3 points. Right. For example, P, Q, and R. So when we have 2 points, we have a vector. We have another 2 points. We have another vector. When we do the cross product, we have the normal vector to those two. And that is the normal vector for the plane. And after that, we have the vector and the point. We have a plane. So, anyway, when we have those 3 points, we can find vector PQ. Q minus P. So 1 minus 2 minus 1. 4 minus 1, 5. And 0 minus 3. PQ and PR. PR. R minus P. R 0, -1, and 5 upon P 2, -1, and 3. So that gives us -2, -1, negative. That's 0. 5 minus 3, 2. So we have those 2 vectors. When we have 2 vectors, do the cross product. We have a vector that is orthogonal to both. So orthogonal to the whole plane. Therefore, we call that the normal vector. So the normal vector equal to PQ cross PR. Or PR cross PQ. Doesn't matter. Remember, when we have a plane, we have the vector pointing this way or the vector pointing that way. As long as it is normal to a plane, it is fine, right? So we have a plane, could be vector point this way or vector point that way. Still the same plane. PQ, IJK first, that's the cross product. -1, 5, and -3. -2, 0, and 2. It's normal. Just the cross product. For I, 5, -3, 0, and 2. I minus for J, -1, -3, -2, and 2. And then for K, -1, 5, -2, and 0 for K. Right. So for I, 10, -1, so that's -2, -2, -2, -6 is -8, and then it's an extra negative, so that's +8, and then nothing, -10, but this shows +10 actually. Yeah, so that is the normal vector. And then we put into the equation. By the way, which pawn do we use? We have 3 pawns, so we can use any pawn we want to. Let's go with this pawn. Right, it has a 0. Sorry. And then the equation is going to be we have the vector n going to be the dot product with vector p of whatever that pawn and the vector connecting that to another pawn. So we say x minus that pawn, y minus that pawn, and z minus that pawn. Equal to 0. Right, multiply this out. By the way, n is those x minus 1, y minus 4, and z. So we multiply it, we have 10 x minus 1 plus 8 y minus 4 and 10 z. Equal to 0. So multiply it all out, we have 10x minus 10 ay minus 32 plus 10z equal to 0. Since all of these are even, why don't we divide everything by 2? So that simplifies a lot, right? And then 10 minus 32 is minus 42, right? Yeah, and that divided by 2 as well. So bottom line we have 5x ay divided by 2, 10z divided by 2, and that is 42 divided by 2 is 21 equal to 0. So yeah, so that is the equation of a plane. And in the book they write like this, so it's just move to 21 on the other side. It's perfectly fine. Right, so that's what we have. Simple enough, right? So we have a pawn and a normal vector. In that case we have a plane. Or we have 3 pawns that are not on the same line. If we have all 3 pawns on the same line, the cross product equal to 0. We don't have the normal vector. So those 3 pawns cannot be on the same line. Right. If we have the vector, all of them, so we take this vector and cross with that vector, that will be 0. The cross product will be a 0 vector, right? Or the magnitude equal to 0, because the sine of the angle between them, sine of 0 is 0, and the cross product, magnitude of the cross product is equal to the product magnitudes times sine of the angle between them. So the magnitude is equal to 0. We don't have the normal vector. Right. Or in terms of right-hand rule, we have to have 2 vectors. So the first vector, and then we can curl the finger into the second one. In that case, we have the thumb as the cross product. If we only have 1 vector, so if we're not curling the fingers, in that case, we can just turn anywhere, because when we turn, we fix the thumb. If we don't curl the fingers, we don't know if the thumb is fixed this direction or that direction, so it can turn. Right. So we see that the coefficient of x, y, and z extract from that give us the equation that we mentioned before. If this equation we can extract, we have the 5, the 4, and the 5. That is the normal vector, which is the same as 10, 8, and 10. So from the equation, we just extract the coefficient of x, y, z, give us the normal vector. So first, if we have this equation, find the vector normal to Q. Easy. Just pick out the coefficient. So normal vector is equal to 2, -3, and -1. The coefficient of x, y, and z. Right, next, find the point Q intersect the coordinate axis. So the coordinate axis is the the x-axis or the x-intercept. X-intercept is when x equal to 0. Sorry. X-intercept is where y and z equal to 0. So if y and z equal to 0, we have 2x equal to 6. So x equal to 3. So we have the point x equal to 3, y equal to, that really confusing, y equal to 0 and z equal to 0. Likewise, y-intercept, the other two equal to 0. So we will have -3y equal to 6. So y is equal to -2. So we have x equal to 0, y equal to -2, and z equal to 0. And then z-intercept. For z-intercept, x and y will be equal to 0. So x and y equal to 0, -z equal to 6. So z equal to -6. And we have the point 0, 0, and -6. So that gives us the x and y z-intercept. Now, describe the set of points at which Q intersect with the xz plane. So, on the xy plane, the intersection, the other variable equal to 0. So we have z equal to 0. We have 2x minus 3y equal to 6, which is a line. Makes sense, right? We'll have a plane on. So I might, yeah, let me just write everything down, then I will draw down. Draw it later. YZ plane. For YZ plane, x will be equal to 0. We have -3y minus z equal to 6. That also a line. And finally, xy, yz, we haven't have what? xy, yz, and xz. That doesn't make any sense. XZ plane. For XZ plane, y equal to 0. So we have the plane 2x minus z equal to 6, which is also a line. So think about this. I'll just draw a sketch real quick, three-dimensional. X, y, and z. We might have a plane like this. So intersection, of course, we have the x-intercept, y-intercept, and z-intercept. And then we have the intersection on the xz plane, a line. On the xy plane, it's also a line. And on the zy plane, also a line. So that's what we have. This is a plane. Of course, that is extended in every direction. Right, that's good. Right, next, two distinct planes are parallel and then orthogonal. So let's say we have two planes that are parallel. Right, parallel plane. Of course, you cannot see like that, so I'm going to put two planes parallel like this. Of course, two parallel planes, what they share is the common normal vector, right? Pointing in the same direction. However, the vector can be extremely long or extremely short. We don't know that. What we do know is if the planes are parallel, the vectors are parallel as well. So, two distinct planes are parallel if the two normal vectors are parallel. Now, two perpendicular planes. This is perpendicular. Each one of them has a normal vector, right? So this plane has a normal vector in this direction. And this plane has the normal vector in this direction. Right? Think about the two planes. This plane here has the normal vector. This plane down here has a normal vector. So the normal vector will be orthogonal as well. So what we mean is two planes are parallel, two distinct planes are parallel if the normal vector are parallel. Two planes are orthogonal if the normal vector are orthogonal. Right. So if the two planes are parallel, the normal vector are parallel. If the two planes are orthogonal, normal vector are orthogonal. Their respective normal vector, I forgot to type, normal vector are orthogonal. Of course, orthogonal meaning the dot product equal to 0, and parallel meaning that one is the multiple of others. So when we're talking about parallel vectors, could be this short, could be that long, or even on the opposite direction. All of them consider parallel. Right. Which of the following distinct planes are parallel? So how do we do this? We have about 3 planes here. So just pick 2. How about Q and R? Q and R. We just extract the vectors. The vector for Q. So I'm going to write n normal vector of Q. And we extract the coefficient of x, y, and z. And then for R, we write normal vector for the plane R, -1, 3/2, and -3. So notice that if you multiply -2 from here, give us 2, -2, give us -3, -2, give us 6. So I'm just going to write since NQ is equal to -2 and R, so one of them is the multiple of other. So we have the normal vector NQ parallel to NR. If the vectors, the normal vector are parallel, the plane are parallel to. I just use this notation for parallel. Alright. And then Q and S. We still have NQ, 2, -3, and 6. And then NS, 6, A, and 2. Look like they're not a multiple of each other. So if they are not parallel, are they orthogonal? So let's check real quick. NQ dot product with NS, 2, -3, and 6, 6, A, and 2. Dot product give us 12 minus 18. if I multiply correctly, it would be 24, 3 times 8. And minus 12. That is equal to 0. Now if the dot product equal to 0, meaning that they are orthogonal. So we have NQ dot NS equal to 0. So we have NQ orthogonal to NS. If the normal vector are orthogonal, the plane will be orthogonal. So Q, again, I've just used that notation. Maybe not correct one, but we mean that means orthogonal. And then of course we can do S and R. Will be done similarly. So to see if they are parallel, if they are multiple of each other. If not, the dot product is the dot product between them equal to 0. If it is, they are orthogonal. The vector are orthogonal. The plane will be orthogonal as well. Right. Next, find equation of the plane Q that passes through the point -2, 4, and 1. So suddenly we have a point here, which is good. And then parallel to this plane. Now, if it's parallel to that parallel planes, the normal vector will be parallel as well. So for R, normal vector for the plane R, we extract the coefficient here, 3, -2, and 1. Parallel planes have parallel normal vector. So normal vector for the plane Q parallel to NR. So we can use this vector, or we just use any multiple of NR is fine. So NQ equal to, just say the multiple of the vector, normal vector of the plane R. I just choose K to be 1. So we have NQ is equal to NR. And then we have a plane where we have a vector, now the same vector, subtract the vector difference between x, y, z, so I just say x, and that's the point, right? Just point. It's always x minus -2, y minus 4, and z minus 1, on which equal to, so dot product equal to 0. So in this form, so always the normal vector and then x, y, and z minus the point. So I usually write the equation of plane in this form, or I multiply it out, 3x plus 2 minus 2, y minus 4, and then 1 times z minus 1 equal to 0. Yeah, usually I prefer to write the equation of a plane in this form, so we can get the normal vector and the point quickly. So that's good. Right, next question. Find equation of a line that is the intersect of those two. So there are a lot of ways to do this. I come up with 2 right away. So let's say we have 2 planes. When we set up this intersection, x equal to x, y equal to y, z equal to z, or meaning that we have the system of 2 equations. So why don't we just solve the system of 2 equations? See what happens. Right, so we have system of equation x plus 2y plus z equal to 5, and then 2x plus y minus z equal to 7. So that is the system of equation. It's not enough. Usually when we have three equations, three variables, that is the standard, right? And we have two. So there might be some things here. So what do we do? Let's just put in the calculator and do RIF and see what happens. There's more than one way to do this, but I just use second matrix, math, reduce row echelon form, and let's put the matrix, alpha, zoom. Little different here. How many? There are two rows because of two equations. So two rows, how many columns? One for x, one for y, one for z, one for constant. So there will be 4 columns. So it will be 1, 2, 1, 5, 2, 1, -1, and 7. Alright. Right. So just say I will do reduce row echelon form. I will have the system 1x, 0y, minus 1z equal to 3, no x, 1y, plus 1z equal to 1. Right? And then from here we can solve for x, right? X equal to z plus 3, y equal to minus z plus 1. That's what we have, right? Of course, in here, two equations, three variables, so we can choose z to be arbitrary. Usually that is the case. So we choose z to be arbitrary. For example, let z be t. So if we let z equal to t, so we have x equal to t plus 3, y equal to minus t plus 1, and z equal to t. Or we can say x, y, z is equal to t plus 3 minus t plus 1 and then t. Yeah. So this is the line of the intersection of two planes. So I have two planes, they might be a line that go through like this. Yeah. So that is the line at the intersection of the two planes. Right? Now, so we're trying to find the equation of this line. So another way to do this is when we have a plane, there is a normal vector, right? By the way, the plane doesn't have to be perpendicular. The plane could be, they might not be orthogonal. They might be just like this. So if I have a plane, there will be a normal vector. If I have another plane, there will be another normal vector. So two normal vectors for two planes. If I do the cross product of those two vectors, the cross product of these two vectors is that, right? The cross product of the two vectors is the vector that is orthogonal to both. So pretty much I can find the vector of this plane and the normal vector of that plane, do the cross product, going to give us the vector that is in the direction aligned with the line L. So this is one way to do it. Another way to do this is direction vector for the line, for the intersection line. Is parallel to, yeah, we don't have to say it is the same. In general, it just needs to be parallel to the NQ cross NR. So when we have two plane, as you see, NR and NQ for two plane, when we do the cross product, we have the vector that on that is the direction for the line L. So we just do the cross product NQ and NR. Alright, for this equation, NQ is equal to, just pull out the coefficient of x, y, and z, 1, 2, and 1. And in the normal vector for R, 2, 1, and negative 1. So we just do the cross product. NQ cross NR. I, J, K, 1, 2, 1, 2, 1, negative 1. So cross product. Yeah. 2, 1, 1, negative 1, I minus 1, 1, 2, negative 1, J plus 1, 2, 2 and 1, K. So 2 times negative 1 is negative 2, and negative 1, so that's negative 3. Next, negative 1, negative 2, negative 1, negative 2, negative 3, but with an extra minus, so that is a 3. And then 1 minus 2 times 2, so 1 minus 4 minus 3. So when we do the cross product, we have this. But remember, like we did this earlier, when we have the vector, and if we just need the direction, we can just multiply something or divide by something to turn this to something similar. So we can choose the vector parallel to this, so why don't we choose divide by 1/3? So we will actually choose direction vector we can just scale back to, say, negative 1, 1, and minus 1. It's fine, right? And finally, we do need a point. How do we find a point? Now that's kind of difficult to find the intersection, right? Yeah, so we cannot just pick any random point to work. So intersection, whatever point is, has to be intersection of those two planes. So from here we cannot actually pick any point for intersection. What we have to pick is something in here. Let's T to be let's give this for the intersection. Let's choose T to be 0 for the intersection. This looks simple enough. So we have T equal to 0, right? So we have the point 3, 1, and 0. And finally, when we do this, we can say the equation of intersection is R naught plus TV. R naught we're going to use, I don't know what I write here, but the intersection is going to be that 3, 1, 0, and then plus negative 1, 1, negative 1 times t. Of course, t is between infinity and negative infinity to infinity. By the way, when you multiply now and combine, this equation will be very similar to that. By the way, when we talk about the direction vector, it could be very small vector or very long vector, or even point in the opposite direction, as long as it is on the same line. Same thing for the normal vector. We can talk about a very short vector, or very long vector, or even in the opposite direction. As long as it aligns on a line, we can use those vectors. So that's why in here I can choose simplicity. I just divide everything by 3, or I can divide everything by negative 3, or I can multiply by 10. It doesn't matter. Any multiple of this is fine. So that's why we can choose the direction vector to be something more convenient. I can just actually choose that, so I don't have to do anything. I can just choose this to be the direction vector. So I have negative 3, 3, and negative 3. Work out just fine. Any vector will do. Right. Sorry, this kind of a long section, but at least we'll cover some very important and interesting thing. We did not go to, we haven't done any calculus yet, but this preliminary material is very important. So anyway, I stopped the section here because I covered everything I need to. See you in another video in Calculus 3. As always, thank you for watching.